Welcome to the rigid body equations of motion. Today we are going to discuss the inertia tensor and the moment of inertia. The operator I that we've encountered previously is known as the inertia tensor. And we would like to express the kinetic energy in terms of it. Now, the definition of the kinetic energy for a system of particles is given here, where I've assumed that there is an implicit summation given by Einstein's convention over indices that repeat twice. However, in situations where we have expressions that will involve repetitions of indices that go 3 times or more, I will write the sum explicitly. So it should usually be very clear when it is implicit. I will write it explicitly just to avoid confusion when the index is repeated more than 2 times. And to avoid confusion, I will try to specify when summation is neither written explicitly nor implied, but it should usually be fairly obvious from the context where it applies and where it doesn't. So this is the definition of the kinetic energy for system particles, and if we apply equation 5.2, we can cast it into this form, which immediately allows us to explicitly construct the total angular momentum of the system. And as we've already seen, the angular momentum is obtained from the contraction of the inertia tensor with the angular velocity. So the scalar t, the kinetic energy, can be obtained through this double contraction of the inertia tensor. Now, the angular velocity itself is oriented in a specific direction, and then the expression for t that we have obtained above can be written as here. And what this allows us is to write the explicit contraction of the inertia tensor in terms of a scalar quantity I, which is known as the moment of inertia about the axis of rotation. And using the definition of the components of I that we have written down explicitly in the previous sections, we immediately find this expression for the moment of inertia, where once again the implicit summation is understood over the particles of the system. That was an interesting observation. Newton's second law and for the angular momentum, together with the kinematical law 486, says that the torque applied to a system of particles is equal with the time derivative of the angular momentum in the body set of axes plus this cross product. But now if we take the dot product of this result with the angular velocity, we obtain the expression here, because this term vanishes since it is perpendicular to the direction of omega. And then for the left hand side, really this time derivative of the angular momentum is just equal with this expression, so we can then immediately include the dot product here under the derivative, and really what we have obtained is just the total time derivative of the kinetic energy, which leads to the result here. So the time derivative of the kinetic energy, which is a scalar quantity, is equal with the dot product between the angular velocity and the applied torque. Now, in an elementary treatment, the moment of inertia about an axis is defined as the sum over the particles of the body, this shouldn't be here, of the products between particle masses and the square of the perpendicular distance from the axis. So written simply, it's the expression here. And we have to show that this is equivalent with the definition that we we have obtained just on the previous page, so the one given here. And it is in fact quite simple to see that, because if we just multiply and divide by omega, we can immediately obtain the explicit expression of the velocity vectors for each particle, and then really this amounts to this relationship between the free scalar quantities, which is exactly what we have obtained from our own analysis earlier. Another way to look at it is to simply expand the dot and cross products and calculate everything explicitly, and it's very easy to do so. You will obtain this expression right away, where the x's are for each particle I are the three components of its of the particle's radius vector, and the n with indices are just the components of the axis of rotation. And of course we know how to contract two Levitch beta symbols to obtain the formula here, which we can finally contract into the definition of the moment of inertia that we have developed earlier. Now, the moment of inertia is a constant only when the body rotates about a fixed axis. In this situation, the kinetic energy as prescribed by result 516, so the one here, is almost in the form required to furnish Lagrangian equations of motion. The one needed element is an expression of omega as a time derivative of an angle. This is something that we will get back to a bit later, but now there is another important point that we have to prove regarding the moment of inertia, and it follows from the fact that we can write the radius vectors of the particles as given in the laboratory system. We can write them relative to the center of mass of the system through the expression here. So if we use the elementary definition of the moment of inertia, and we just expand the radius vectors according to this result, we obtain the formula here, and then we can of course just expand further and write the terms out explicitly. So the term containing the center of mass of the system, this will involve a summation just over the masses of the particles. So they add up to the total mass of the system. Then the term involving these radius vectors has exactly the form that we would expect for a moment of inertia, but it's given about some other axis. And then we have the dot product here, which by a little manipulation can be shown to be immediately equivalent with this expression, and this thing vanishes. It vanishes because the summation here adds up to 0, as these are the relative positions of the particles to the center of mass added up in the system of the center of mass. So this thing vanishes. And what we have obtained is the expression here, or if we write the cross product explicitly, the result here. So the magnitude of the cross product between the center of mass of the system and the axis of rotation is given in terms of the angle theta between r and n, and is the perpendicular distance of the center of mass from the axis passing through O1. So the moment of inertia about a given axis is equal to the moment of inertia about a parallel axis going through the center of mass plus the moment of inertia of the body as if concentrated at the center of mass with respect to the original axis. So just to identify things, this is the moment of inertia about a given axis, and it would be equal to the moment of inertia about a parallel axis going through the center of mass, which is this one, plus the moment of inertia of the body as if concentrated at the center of mass with respect to the original axis, which is the term here. Furthermore, we can then write what is the kinetic rotational energy in the form here, which we can expand immediately into this expression if we work out the square of the cross products, and if we use the definition that we have derived earlier in terms of the angular velocity and the inertia tensor, these two are equivalent if the inertia tensor has these components. And this is written for a system of mass points, but we can generalize the definition immediately to a continuous mass distribution to obtain the formula here. So these components, alpha and beta of I, are the components of the moment of inertia tensor. And as a final comment on this topic, if we can associate an antisymmetrical matrix to the coordinates of a given particle I, as shown here, so these are the components of the matrix, which is manifestly antisymmetric. And then if we assume that the components of the inertia tensor are given by this expression, if we expand this out immediately and carry out the contractions, we discover that this definition is entirely equivalent to the ones that we have obtained previously. As an example, we can consider a cube of homogeneous density ρ, mass m, and side a, with the constant b defined as the product between m and a squared. And we can consider that the origin is taken with respect to a corner of the cube. Then if we want to calculate the components of the inertia tensor, the diagonal ones are given, for example, by the expression here. So this is for the x coordinate. This is just the density times the volume integral here, just by applying the definition. And the constant density is, of course, just the mass of the cube divided by its volume. And we can write the volume integral explicitly in Cartesian coordinates and integrate over the cube. So the r squared minus x squared is just y squared plus z squared in Cartesian coordinates. And it's a trivial matter to carry the integration out and discover that the diagonal components will all have this value. Of course, you can calculate them separately for the y and z coordinate, but the result will be the same given the symmetry of the cube. As for the off-diagonal components, once again, these are all equal due to the symmetry of the cube, and you can convince yourself by calculating explicitly. But as an example, for let's say the component xy, if we apply the definition, the expression is the one here, and it closes. It solves immediately into this result. So the components of the inertia tensor, when choosing for a cube, when choosing the origin with respect to one of its corners, has these components. So both the moment of inertia and the inertia tensor itself present symmetry properties with respect to the center of mass that are similar to those found for the total linear momentum, or the total angular momentum, or the kinetic energy of a system of particles, as was discussed back in section 1.2. In summary, we have studied the properties of the inertia tensor and of the moment of inertia scalar. We have derived the theorem of the parallel axis, allowing one to calculate the moment of inertia about any axis of rotation in terms of the moment of inertia about the parallel axis passing through the center of mass. and in the following we will discuss the eigenvalues of the inertia tensor and the principal axis transformation. All that being said, I hope you found the video worth your time. I want to thank you for watching it, and I will catch you later. Goodbye.